Welcome to our celestial battlefield. If you heard of our handmade celestial spheres, then our brave soldier, a celestial sniper, ready to conquer the mysteries of the universe.
Today, we'll follow the soldier mission as they scout the celestial equator, ecliptic, and track the seasonal maneuvers of the sun. He'll also decode coordinates and identify star targets. Let's hear the mission.
First, our soldier surveys the battlefield. The celestial equator divides the sky into two strategic zones, north and south, just like a tactical map dividing territories. The sun path, the ecliptic, is the key target zone. This tilts trajectory at 23.5 degrees to the celestial equator, marks the sun's journey as Earth orbits. It's where the real action unfolds, and the soldiers always keep in their crosshairs. The intersections of these two lines, the vernal and autumnal equinoxes, are like critical checkpoints. They mark moments when the sun crosses into neutral territory, making day and night equal.
Now, let's follow the soldier as they track the sun's seasonal moves. The sun is like an elusive general shifting its position along the ecliptic. At the vernal equinox in March and the autumnal equinox in September, the sun is at the celestial equator, and daylight and darkness share the field equally, 12 hours each. During the summer solstice in June, the sun climbs to its highest point in the northern hemisphere sky, shining over the Tropic of Cancer. This is the longest day and shortest night, a perfect time for extended reconnaissance missions. Conversely, the winter solstice in December sees the sun retreat to its lowest point, hovering the Tropic of Capricorn. This means shorter days and longer nights, the ideal conditions for the nighttime operation. The soldier observes that the sun rise and sets angles vary by season. In summer, it rises north of east and sets north of west, extending daylight. In winter, it moves south of east and west, shortening daylight. These shifts determine the timing of every celestial operation.
To locate stars, our soldier uses the equatorial coordinate systems. Think of it as their sniper scope for terrestrial targets. Here's how it works. Declination acts like the vertical aim, measuring how far north or south a star is from the celestial equator. Right accession is the horizontal adjustment measured in time units, tracking the star's position as Earth rotates. With these coordinates, the searchers can precisely target any star in the sky. It's a footproof system.
But the soldier also needs to adjust their aim based on their location on Earth. The horizontal coordinate systems come into play here. Take two examples. 1. Sirius, with a declination of negative 16.7 degree, appears low in the southern sky for our soldier in the northern hemisphere. They aim just above the horizon. And the second one, Polaris, with a declination of 89 degrees, stands almost directly overhead in the northern hemisphere. It's an easy fixed target. Just remember, declination determines how high or low a star appears relative to your local horizon.
Some stars, like Polaris, never set below the horizon for northern observers. These are the circumpolar stars, constant companions in the soldier's celestial battlefield. To find them, our soldiers calculate stars with the declinations greater than 90 degrees minus their latitude remain circumpolar. For example, at 40 degree north, stars with declinations above uh, plus 50 degree are always visible. These stars circle the celestial pole, like loyal sentinels guarding the night sky.
Our soldier has completed their mission with the celestial sphere as the battlefield map. They've targeted the sun maneuvers, pinpointed stars, and identified circumpolar targets.
Happy stargazing and mission accomplished.